Hey everyone, and welcome. Ever wondered what makes your smartwatch tick or how the systems in your car just work? Well, you've come to the right place. We're about to break down the essential skill stock you need to master the world of embedded systems.
This quote right here, it really hits home for so many people. You get excited, you buy a development board, you follow a bunch of tutorials online, and then you just hit a wall. You're stuck. And as this quote says, it's because learning the right topics in the wrong sequence can completely block your progress. It's not about how hard you're working. It's about learning things in the right order. And today, that's exactly what we're going to fix.
So how are we going to do that? We've got a roadmap. First, we'll talk about that embedded learning trap. Then we'll build what I call the bedrock foundation. After that, we're mastering the bare metal, figuring out the bare metal versus RTOS debate. And finally, tackling this super important topic of security. Let's get into it. Okay, first up, the embedded learning trap. This is all about making that leap from just a hobbyist following tutorials to a real engineer who actually understands what's going on under the hood. So does this hit close to home? You've messed around with an Arduino, you've made an LED blink, maybe you even got a sensor to work. But deep down, you still feel like you're just copying and pasting code. You don't feel like an engineer who really gets it. Well, guess what? You are definitely not alone. The problem isn't you, it's the order you're learning things in. So let's start fixing that right now. So where do we start? We start by building your bedrock foundation. And when I say bedrock, I mean it. These are the absolute 100% non-negotiables. You just can't skip this stuff. This foundation rests on two massive pillars. First, the electronics fundamentals, and second, what we'll call embedded C programming. So why both? Well, think about it. Your code isn't just floating around in the cloud. It's running on a physical piece of silicon, literally flipping switches and changing voltages. You've got to understand both the physical world and the software world to make them work together. Now, when we talk about electronics, I'm not talking about getting a PhD in physics. I'm talking about the practical stuff you'll use every single day. Things like Ohm's law and voltage dividers. You literally can't connect a sensor without them. Transistors, like MOSFETs, those are just the tiny microscopic switches that your code is turning on and off. And something as simple as a pull-up resistor can be the difference between a button that works perfectly and one that gives you random crazy readings. And of course, you've got to be able to read a schematic. That's your map. Then there's the other pillar, embedded C. And let me be clear, this is not the same C you'd use to write a desktop app. This is C with the gloves off. You're not asking an operating system to do things for you. You are directly reaching into the hardware. Pointers aren't just a tricky concept. They're how you talk to a specific memory address on the chip. Bitwise operations, that's you manually flipping the individual bits, the ones and zeros, inside the microcontroller's control panel. You have to understand how memory is laid out, what the stack and heap are for, and why a little keyword like volatile is absolutely critical to tell the compiler, hey, don't mess with this, the hardware can change it at any time. All right, once you've got that foundation poured and set, it's time for the really cool part. It's time to level up and start mastering the bare metal. This is where we learn to talk directly to the hardware. No middleman, no safety net. So what in the world is bare metal programming? Well, it's pretty much what it sounds like. Your code is running directly on the processor. There's no Windows, no Linux, no operating system of any kind sitting in between you and the hardware. It is just your code and the raw silicon. And what does that give you? Absolute, total control over every single thing the processor does. Okay, so how do you actually use that control? The secret is something called registers. I want you to think of registers as the flight deck, the control panel for your microcontroller. They're these special little spots in memory that you can write values to, and those values configure everything. The timers, the communication peripherals like I2C, SPI, and UART, the analog to digital converters, you name it. If you want to make a timer count faster, you don't call a function. You go find its control register and you flip a few bits. That's the power we're talking about. You might be thinking, wow, that sounds like a lot of work. And it is, but the payoff is enormous. Why do it? Because you get superpowers. You get that direct hardware control, which means insane performance and efficiency. There's no bloated software slowing you down. It forces you to learn what's really happening, so your debugging skills become legendary. In the professional world, it can mean a cheaper and simpler product. And, maybe surprisingly, because your system is simpler, it's often more reliable and more secure. There's just less stuff that can go wrong. Okay, so now you've got this incredible bare metal skill. this brings you to a major decision point on pretty much every project you'll ever work on. Welcome to the architectural crossroads. Should you stick with bare metal, or should you use an RTOS, a real-time operating system? So let's look at the core differences here. Bare metal is kind of like a simple, super efficient single-lane road. You've got your main loop, we call it the super loop, just running over and over. And then interrupts are like emergency vehicles that can cut in when something important happens. It's lean, it's fast. An RTOS, on the other hand, is like a managed multi-lane highway. It's built for multitasking. It has a scheduler that acts like a traffic cop, giving different tasks, like reading a sensor or updating a screen, their own turn to run. Now, this highway takes up more space, right? More memory, more CPU cycles. But when you have a lot of traffic, a lot of complex things happening at once, it's way easier to manage and keep everything from crashing.
Okay, so that's the big picture. But the real question is, for your next project, which one do you pick? How do you make that call?
Well, it all boils down to your application's needs. If you're building something super simple, say a little battery-powered weather sensor that just wakes up, takes a reading, and goes back to sleep, bare metal is your best friend. It's tiny, it's power efficient, it's cheap. But what if you're building a smart thermostat? It has to talk to your Wi-Fi, update a graphical display, listen for your voice commands, and control the AC, all at the same time. Trying to juggle all that in a single bare metal loop would be a nightmare. That's where an RTOS becomes a lifesaver. It gives you the structure you need to handle all that complexity, especially things like network stacks for Wi-Fi or Bluetooth. We're on to our last and arguably most critical layer of the skill stack. And this is something that, frankly, you cannot afford to ignore anymore. We're talking about security, the new dimension in design. Just take a second and let this quote from Princeton sink in. Security is an entirely new metric, along with cost, performance, and power. What does that mean? It means security isn't some checkbox you tick off at the very end of a project anymore. It's a fundamental design constraint, just as important as how much your device costs or how long its battery lasts. It has to be baked in from the very first line of code. And here's why it's so critical. The moment you connect a device to the internet, or even to another device, it becomes a target. That little smart plug, that connected car, that medical infusion pump, it's no longer an isolated box. It's a potential doorway for attackers. And you have to defend it against everything from clever software hacks over the network to someone literally trying to physically break into it. So what does security actually look like in an embedded system? Well, it's a few key things. It's about confidentiality, making sure no one can spy on your data. It's about integrity, making sure the data hasn't been secretly changed. It's authentication, proving you are who you say you are. It means having secure storage, so an attacker can't just read your secret keys or your firmware off the chip. And finally, tamper resistance, which is about making the device fight back if someone tries to physically mess with it. These aren't just ideas, they are design requirements. So let's wrap this all up. Here is your 4-step roadmap. It's a proven path. Step 1, build that unbreakable foundation in electronics and real embedded C. Step 2, go deep and master bare metal programming so you know exactly how the hardware works. Step 3, learn when to use that skill and when to reach for the power of an RTOS. And finally, step 4, make security a core part of your design process, right from the start. Look, following this structured path is the difference between just dabbling and actually engineering professional, robust, and secure systems. These tiny computers literally run our modern world. So the only question left is, are you ready to be one of the people who builds them the right way,